In this session, we will discuss constrained motion. Now, the reason for discussing this is that sometimes the motion of one particle is dependent on motion of another particle. The simplest example of this we have already seen. If you recall, we had discussed the example where two blocks were connected through a string which was passing over a pulley. So, in this example, we had said that the acceleration of the two blocks will be the same. So, let's once again discuss why. So, for a string, if you look at the length of the string cannot change. So, when these blocks move, let's say that this block goes up by amount x and the other block comes down by an amount y. So when this happens, we are going to look at the effect that this motion is going to have on the length of the string. So now, whenever you're doing such an analysis, I would recommend that you imagine that the string is nothing but a taut rubber band. A rubber band that is slightly elongated and is very taut. Right. So, in this case, when we analyze the effects, we will analyze the effect of one motion at a time. What this means is that we would assume that there is only one movement and everything else is stationary. Right. So, for this case, for example, we would assume that this arm is stationary, everything else is in its place, and only M1 moves up by an amount x. So, if that is the case, think about this rubber band. What will happen to its length? I'm sure you can see that if it goes up by an amount x, the length of this rubber band decreases by the same amount x. Right? Because this arm does not change its length. In the other arm, when you lift this up, the length has shrunk by the amount x. So, whenever the length decreases, when the length decreases, the contribution is negative. So I'll explain what I mean by the contribution. So first understand that whenever some motion causes a change in length, which is a decrease in length, we would take that as negative. On the other hand, if we assume that the left arm is stationary and M2 goes down by an amount y, you can see that this length will increase by that amount y. So in such a cases, when length increases, if the length increases, then the contribution is positive. So now let's talk about why we are calling it contribution. So what we are trying to do here is that though the motion is simultaneous and they bring about their changes simultaneously, we are going to analyze it one by one. So the movement of M1 upwards and M2 downwards, we are going to view it as separate events. And the final event in which both of them move will be seen as a sum of these two events. So this is what we mean by the contribution of M1 and the contribution of M2. Right. So if we were writing these equations for the given scenario, we would first of all focus on M1, that this side remains the same and this side the length shrinks by x. So since the length has decreased, we will call it minus x. Right. Now we will focus on the other side. On this side, we see that if everything else is stationary, this M2 causes the length to increase by an amount y. So this y is the contribution of M2. Now, the sum of all contributions must add up to 0. This is because the length cannot change. So if you simplify this idea, basically what we are saying is that the total change in length of the string can be thought of as the change caused by the first particle plus the change caused by the second particle, and so on if you have n things attached. Right. So in most of the cases, you only have two things changing its length. So if this is the case, we see that x is equal to y. So now this means they are covering the same distance. Now you may also see that they will cover the same distance always in the same amount of time. Now since the amount of time is same, knowing that the distance is same, we can say that the speed of one will always be equal to the speed of 2. And whenever the speed changes, the speed right. So in this case, let's try to find the relation between acceleration of 1 and acceleration of 2. Before we start this, let me already tell you that this is slightly beyond the scope of our normal discussion. So if you find this difficult, I would suggest you keep coming back to this till you become comfortable with these ideas. Right. So now looking at this arrangement, first of all, we can clearly see that motion of M2 will certainly have some relation with motion of M1. It cannot move independent of M1. So this is why their motion is constrained. And we are trying to find the relation between the motion of M1 and motion of M2. Right. Again, to do that, we will use the fact that these strings are inextensible. So in this case, we will focus on two strings. Let's name them. So this is the first string, we'll call it S1. You can see that as it moves down, this pulley would go up. On the other hand, if this was going up, the pulley would come down along with M2. Right. So let's start with a simpler case first. Let's focus on string 2. To do that, let's look at the contributions. Let's say that the side on which M2 is going down. So let's say that M2 goes down by an amount X and this pulley comes down by an amount Y. Now, focus only on the string 2. Assume everything else is fixed and you don't need to look at string 1 while you're discussing string 2. So right now, keep your attention only on string 2. Now first identify the things whose motion can affect the length of the second string. You can clearly see that it is M2 and pulley 1, right? Because motion of M1 does not directly change the length of the second string, right? So let's now write contributions. So if everything else is stationary and M2 comes down by an amount X, the length of the second string will elongate, it will increase, right? And it will increase by an amount X. So the contribution of M2 is plus X. The plus indicating that the length will increase, right? Once again, if you keep M2 in its place, keep everything else in its place and bring the pulley down. If the pulley comes down by an amount Y, the length of the string will decrease by this amount Y, right? Focus only on the second string, not on the first string, right? You're not concerned with the effects on the first string. We are only writing the equation for the second string, right? So if M2 is held fixed and the pulley is brought down, the length of the second string decreases by an amount Y. And the sum of these contributions should be 0. So we get that X is equal to Y. So this is our first equation which we have got through string 2. Now let's focus on string 1. Now string 1 is slightly more tricky. This is because this involves a movable pulley. Let's see how. Let's first of all assume that M1 is going to go up by an amount Z. This is again obvious. If this side is going down, this side would certainly go up, right? So once again, we are going to write the contributions for string 1. So we can see that the two things that will change the length of string 1 is M1 and pulley 1, right? Because pulley 2 stays in its place and M2 is not even connected to that string, right? So first of all, look at M1. If everything else is kept fixed and M1 goes up by the amount Z, this rubber band will decrease its length by the same amount Z, right? Because if everything else is fixed, this goes up, the length decreases by Z. So its contribution is minus Z. Now, think about this pulley. Let me redraw it. So once it has gone down by the amount Y, the pulley would be somewhere here, right? The center would have gone down by this amount Y. So if everything else is in its place, when this goes down by an amount Y, you would see that thread would elongate by an amount Y on this side and also by Y on the other side. So when the pulley goes down, it brings the thread with it on both the directions, right? So we see an elongation, but that elongation is brought about on two sides, on the left as well as the right, and hence the total change that this brings about is plus 2y. We've taken plus because there is elongation, and 2y because as the pulley moves, it changes length from left side as well as from the right hand side. Now, once again, these two contributions must add up to 0. If that is the case, we see that Z is equal to 2y. And this is the second relation. So now once again, we have found the relation between the distances moved. But we know that all these distances will be covered in the same amount of time. So what can we make from that? We can say that acceleration from this relation, that x equal to y, we can say that acceleration of 2 will be equal to the acceleration of pulley, right? We can also say that velocity of 2 is equal to velocity of pulley. Both these things come together. This is because the same distance is covered in the same amount of time, and hence any change in velocity is also brought about in the same interval of time. So for mass 2 and this pulley, we can say that the velocities as well as the accelerations are the same. Now, looking at the second equation, we see that Z is equal to twice of Y. What does that mean? Z is related to the motion of M1. Hence, we can say that V1 is equal to twice the velocity of pulley and is hence equal to twice the velocity of the second mass. And similarly, acceleration of 1 is also twice the acceleration of pulley and hence is equal to twice the acceleration of A2. Once again, we see that the relation of displacement directly translates to the relation between the velocities as well as the accelerations. So once this is done, we have the final values which we were looking for. That is, we have a relation between A1 and A2, and we see that A1 is equal to 2 times A2. So during any motion on this arrangement, whether this side goes up or that side goes down, whichever direction this moves in, there will always be a relation between their accelerations. That is, the acceleration of 1 will be twice the acceleration of 2. And this is why we separately study constrained motion, because it does not depend on the forces or the masses. This is a result of the arrangement that we have created. The geometry of this dictates that the acceleration must have the relation that A1 must be twice the acceleration of mass 2. Right. So with this, I hope you've understood constrained motion. So these constraints give us sometimes the additional equations required to solve the variables. But at our level, we would have very few problems which involve such constrained motion. But this is very critical when you go and do problems in the higher levels. Right. So with this, we've also come to the end of this chapter. I hope you enjoyed learning about the laws of motion. Thank you.